do it like that. Okay, so first class, Marianna will explain us also, there is a website, etc., etc. She will tell us, is on the challenges of detecting ultralight dark matter, and I leave the stage to Marianna.
Thank you so much for the introduction. Oh, an invitation. Can you hear me okay? Excellent. Not too loud? So first, I am actually an atomic theorist. So my expertise is in quantum sensors, atomic computations, and specifically search for various new physics with quantum technologies. I also teach quantum information. On my website, you can actually get a link to my quantum information course with 20 lectures if you're interested in that subject, which is not the topic of my talk today. So, and we are going to start, since this is the first lecture and the school is on the fundamental interactions, on grand challenges of particle physics. And let's remind ourselves that 100 years ago, people thought we already knew everything about the universe. And I would like to point out that it's great if you ask questions. We are going to have in-class activities and out-of-class activities, but please ask questions. You will learn more. Okay, sorry, not summer, the winter school will be more fun for you, and you will stay awake, especially for the international participants who are jet-lagged. So it's also a great practice for the future. So the physics is done by discussions. So every time we go, we ask questions, we talk to each other. So it is a great practice for you, especially for the students in their first and second years. Okay, and now let's go back 100 years, as you have given a fantastic historical also overview. This is such a great place. And 100 years ago, we thought we knew everything. There was so much new technologies. There was, trains and automobiles and planes, and we had electromagnetism and statistics and thermodynamics, and people thought that's it, right? People seriously thought, not just like a general population, but scientists, that all we have to do now is to get to some decimal, place. And at the same time, there was those atomic spectra, which people did not understand. And there were many other things people did not understand. And somehow they could have just swept under the rug for just a little while. And of course, from solving those fundamental problems of that time, that's where we got the quantum mechanics. In fact, this is why we are here at the talk of quantum technologies tabletop experiments. And our technology is so significantly affected by the quantum mechanics. It's hard to imagine that at that time, no one thought that solving those fundamental problems could result in anything like this. Even 50 years ago, people had no idea that's where we're going to be. And now we are back to full circle. We have the standard model. And we have also a number of various fundamental physics postulates, which we kind of, when we compare experiments, forgot that those are assumed. We assume Lorentz invariance. We assume the positional invariance. We assume the fundamental constants are constant. But all of those things have to be experimentally verified. And of course, we know already there are many problems with the standard model. And I think this is where we are going to start. Now, it's going to be very boring if I'm just going to talk for 10 hours. So I would like you, every one of you, get a piece of paper or your notepad or anything, and write down what are the problems with the standard model that you know. So why do we want a BSM physics, beyond the standard model physics? And think about things which you really know are wrong with the standard model. For example, I mean, you see those Higgs and neutrinos underlined. Of course, there are many other things which are just not a part of the standard model. And then, of course, there are puzzles and experimental inconsistencies. So write down everything which you know. And I would like you to start doing it on your own. And then when you're kind of done, turn to your neighbors and cross-check the list. So we'll have maybe a few minutes on that. And if you have any question, raise your hand and I'll try to kind of at least come your way. It's a bit difficult, of course, with this classroom. And then everyone will say at least one until we kind of run out of the list, and I'll just write them on a board. And then we'll try to sort them out to different classes. Excellent. The chat. Few people are done. So if you're done, then compare the list to your nearest neighbor. If you are not done, then continue writing. If there is the kind of a three people neighbors, that's perfectly fine. Just a little bit quieter. Okay, that maybe was not well thought out. Okay. Okay, so they've been, okay. And now we would like to combine all of the lists and get them to the board. So I'm going to get some chalk. And a first volunteer, just raise your hand and say one of the problems. Puzzles. Okay. What? Neutrino masses. Okay. Excellent. And as you see, neutrinos are here. And how many people could explain solar neutrino puzzle? Raise your hand. Okay, raise your hand more so I can actually see. Really? Okay, so this is why we know that neutrinos have masses. Because when the people first detected neutrinos from the sun, they did not get enough of them. And this is a fantastic experiment. They literally count neutrinos like 1 neutrino, 2 neutrinos. I think over the lifetime of that experiment, I think they counted 2,000 or so. And of course, you will hear experts talk about neutrinos, but this is such a fantastic puzzle. And people literally think maybe something is wrong with the sun, because they were only seeing a third of neutrinos which they calculated should have come from the sun. And that lasted for years. The more neutrinos they have, that didn't make it any better. And eventually, as people converged, and there really have been massive explanations. First, of course, I'm a theorist. And the first, of course, explanation is blame the theory. There is just theory is wrong of how many neutrinos should be coming from the sun. And that's been recalculated, and no, that's definitely right. And then, of course, experiment, okay, they build nice experiments. And they still see the three different experiments, we're still seeing 30%, about 30% of predicted. And it's not like sigmas, it's like you're not seeing 2/3 of them. And then the explanation was that when neutrinos are produced in the sun, which neutrinos are they? The electron neutrinos, right? So, and neutrinos mix. By the time they get to Earth, you have actually neutrinos now converted to mu neutrinos and a bit to tau. And those experiments could not detect mu neutrinos, they could only detect electron neutrinos. So they built a new experiment which detected all of them and the electron one separately. And they got 100%. And that's actually a fantastic quantum mechanical explanation. Because essentially, you do get neutrino mixing. And it's not possible to generate neutrino mixings if neutrinos have 0 mass. And in a standard model, they do not have any mass. So this is, therefore, a result of solving a puzzle, which lasted for a long, long, long time. That's you can see, I think, the Nobel Prize explanation for this is fantastic. So neutrino masses, why is that a puzzle? The puzzle that we don't know the origin of neutrino masses. I mean, it's not difficult to adjust the standard model to get neutrino masses. We just don't know which of the possible scenarios actually is the right one. Okay, there are many other things we don't know about neutrinos, and there are many other, separate neutrino puzzles in various experiments, which also don't match with each other. Okay, excellent, neutrinos. What else? Raise your hand, anyone else? Okay.
Does not include gravity, the explanation for gravitational forces?
Gravitational force, the nature of gravity. Fantastic, okay. There is a reason why I'm going to write them in different place, and we may or may not agree with clustering of those things. Sorry, it's very hard to hear from the mask, but we should all stay safe. So I'm sorry if I... nature, and the sound seems to be drifting up rather than down. Okay, and the nature of gravity actually, it's a very big question, because as you see in the standard model, we really do not have explanation of quantum field theory of gravity. We do not really have gravity connected to standard model. We can sort of do some tri-effective theories, but we really, gravity and the quantum mechanics as of now do not mix. And this is also some of the parts of the puzzle. What is the nature of gravity and whether gravity is quantum? In fact, it's a very interesting question. How do you design an experiment to prove that gravity is quantum? This is actually a very difficult question to which actually I do not know the answer. Like, if you could do anything, how would you prove that gravity is quantum? And by the way, if you think that you can do some sort of version of photoelectric effect, the photoelectric effect by itself actually does not prove electromagnetic field is quantum. There is a long 50-year discussions on this. So there are papers down to 70s discussing how that actually works. Okay, next. I've seen several hints, okay? The hierarchy problem. Which one? Okay. Okay, the Higgs. Okay. And I'm just going to put the Higgs mass problem. It's formulated in different ways. So, I mean, it could be formulated also as to why the different strengths of different reactions is so different. But the very specific problem is why Higgs mass is so low. And I actually will show specifically why this is a problem, and the Higgs is a scalar. So any correction from, say, a top quark loop, I'll show you the loop, we'll go over those in some more detail, will make it very large. And then, of course, having many different diagrams, cancel to nearly zero is very hard. The other problem that the value, therefore, of the vacuum, of the expectation value of the Higgs field is small. And if you try to put some natural, some initial conditions and make our universe, you generally end up with two scenarios, which are natural. The first one is which is a Higgs field is off, and all masses are 0. Second scenario, in which a Higgs field is turned on fully, and then all masses are at Planck scale, and we end up with lots of black holes instead of particles. Both those scenarios, it's kind of easy to come up with if you're trying to make up a universe. Our universe is not natural. It's extremely fine-tuned to get Higgs where it is. So it's an interesting question whether there has to be an explanation or not for it, which we'll discuss in the future. Excellent. Okay, I saw a hand over there. Yes?
Okay, the ratio between matter and antimatter.
Sorry?
The difference between the quantity of matter and antimatter.
Yes, matter-antimatter symmetry. Thank you so much. Okay. What did I do with the chalk? Okay. Okay, this one is obvious. Our universe, according to the standard model, should not exist. For the very simple reason that in a standard model, you are producing matter and antimatter. At the early universe, it's pretty much the same ratios. And what happens when matter and antimatter meet? Okay, they annihilate, and you have a beautiful universe full of light. Not us. So, for some reason, for the billion of the particles, antiparticles, there was a 1,000,000,001 particle. And when everything which could annihilate did, before the universe expanded sufficiently, you had this one particle left. That had been tested. People have looked for antimatter galaxies, literally. This is a very beautiful and very significant signatures which you really cannot miss. You're pretty sure there are no voids with antimatter galaxies anywhere. People also looked for primordial antimatter. They didn't find any. It's not there is some antimatter. In fact, actually, if you have a thunderstorm, you will get some positrons there. We are talking about primordial antimatter, and we did not find it. So for that to happen, you need to have much, much more CP violation in a standard model than you have. That's a charge parity violation. So this is really an observational problem, which is glaringly obvious because we would not be here otherwise, and we have no idea how to actually solve this. And also you can say, when you say baryogenesis, that's pretty much what our problem is. What's the mechanism for this? Okay, go ahead. Foundations of quantum mechanics. And this is an interesting question which separates too many other questions. And there are several questions here. One of the more simpler ones is quantum mechanics actually linear? What do you think happened experimentally when you add nonlinear terms to quantum mechanics? There is actually one very interesting experimental signature, and people have looked for that recently with actually quantum experiments. When you have a potential, let's say you have a harmonic oscillator potential. You have state 0 and state 1. And you have different versions of the wave function. The one which you have 50-50, and then the other one when you have something else. Let's say 20-80%. Now, do you think that it makes a difference to the energy levels in linear quantum mechanics? Yes or no? Doesn't matter in which superposition is the wave function. No. Because energy levels, you just solve your Schrodinger equation for harmonic oscillator, you get the energy level. It makes no shred of difference what the wave function superposition is. It does if quantum mechanics is nonlinear. So if quantum mechanics is nonlinear, you will have a different energy shift between E1 and E2. And that actually has been recently tested by the actually quantum computing group by Hartmut Hafner, who had actually was very surprised that that's something people have been looking for. And being a quantum information people, they could control the superposition perfectly to many decimal, to at least 4 decimal places or more. And they actually found to the level of 10 to the minus 12, there is no energy difference. So that was one of those tests, for example, for linearity of quantum mechanics. So this is more of a straightforward question. You can actually test for that. There are other effects. And this is kind of the most simple thing. You just add a quadratic term and see what actually it does, and that will be one of the effects. Now, much more complicated questions is, does quantum mechanics actually breaks down? And not that it just breaks down because eventually your quantum system gets larger and larger and larger, and any photon which scatters is going to actually mess with your superposition. I'm not talking about that. The question is there any fundamental reason why quantum mechanics eventually break down when you have a larger and larger quantum systems? And this is really the ultimately, if we ever get to the point that like quantum computers, that could be one of the reasons why it can't be done. If somehow when you actually put more and more quantum systems together, even if you can perfectly control them, if you can perfectly isolate them from environment, it's possible there is something in our universe makeup that eventually it will break down. We simply do not know. So in the other way, what people have tried to do is you have more and more larger microscopical superpositions, you still have interference patterns. People that they soon be able to interfere pretty much something as large as viruses. So, and this is one other test, and something interesting may happen about 10 to the 8 mass units, and they've been tests like this. But theoretically, we simply do not know. If there is any reason that wave function collapse for whatever other reason, for example, if somehow there is a connection to gravity which we do not understand. So this is a very, very interesting question. What I covered, discuss the foundational quantum mechanics, some other subtopics for the suggestion. Yes, the philosophical question, for example, also, I was talking about entanglement, for example. How does it actually work? Right, and with entanglement, okay, you can either take that it's a Feynman's approach, okay, people, you just roll the wave functions, or it's leads to a fundamental question. I've actually recently gave a public talk on a topic because the Nobel Prize was for foundations of quantum mechanics. It was for the Bells inequalities. If anyone interested, I can actually place a link for the talk on my website. But the main issue is that if you make a wave function, zero, 0, plus 1 over square root 2, 1, 1. Okay, this is qubit 1, this is qubit 2, this is qubit 1, this is qubit 2. So this wave function is not separable, it's fully entangled. So if you measure in this thing the first qubit, and this first qubit could be a trapped atom sitting nicely in its no trap. And the second qubit can be another trapped ion sitting in its own trap. It's possible to separate those entangled ions and actually move them apart. And in some foreseeable future, let's say you take one of your nice ion traps and take it to Mars. And another one stays on Earth. And you measure one on Mars, and you find 0. Your ion on Mars just turned to 0. Now, this does not allow faster than light communication for obvious reason. You actually have to call Earth and check what did you get. But the effect appears to be instantaneous. So the quantum mechanics actually works this way is verified by Bells inequalities, and as of now, people close the loopholes there. So that's actually what the current Nobel Prize was for. And at this point, they actually made a lot of tests, and they made sure that all of the other things was uncorrelated, and they really have quantum mechanics works this way. You can actually tell the difference. So, and in terms of the foundations of quantum mechanics, when you make a measurement and you find that your particle is in, let's say, point C, where was this particle before the measurement? And quantum mechanics tell you that it wasn't anywhere. And that's really the foundational philosophical question that the Bell's inequalities and our test shows it's really the way the universe works. It wasn't anywhere. That really there is no hidden variables. There is no theory which can tell you that. And then, of course, there is another series of quantum mechanical questions, and that actually the black hole information paradox. Who knows what that is? Raise your hand. Come on, be braver. If you know, raise your hand like this. Okay. So, keep losing chalk. Okay, let's say you have a black hole. Okay. That is not a black hole, but I want to, okay. I want to draw something which has a horizon. Somewhere on this horizon, that particle-antiparticle pair got formed, and they entangled. One of them, and just before the horizon, one of them got sucked in the black hole, another one was not. There are very significant results of this. And the result of this, that destroys information. And information cannot be destroyed according to quantum mechanics. Now, there are various, and that's why black holes evaporate, because eventually that means a negative mass. Okay, the black holes of the size which I drew is not going to evaporate for any time soon, but in principle, this one mechanism to evaporate the black holes. And that means the black hole can disappear and all information which actually wasn't there will be permanently destroyed. Now, there are various solutions for them, one of the firewalls. And that would eventually mean that the black holes are not true singularities, that there is actually internal structures and there is memory. That actually can be tested. So with more advanced gravitational wave facilities, if there is some structure in the black hole, if there is, not really a true Einstein singularity, there would be an echo in the gravitational wave chirp. Okay, all of that is highly model dependent, but they think the advanced LIGO may have some chance to see it, and like Einstein telescopes could see if that exists. So that is some testing. So there are many other things with quantum mechanics. Did I cover most of the implied things at that point? Okay, yes?
Just for the black hole and the paradox, I don't know much about it, but I've read that the ADS-CFT theory would be a way to solve it.
Yes, as I said, there are solutions for that, definitely. But nevertheless, this is one which kind of hard to experimentally test. And in terms of, there are consequences of non-really normal GR. And that's actually a very interesting connection between quantum information and black holes. People have been trying to simulate black holes with various, Bose-Einstein condensates and so on. And there is some useful information learned from that, but it's unclear, honestly, how you can really port any of this. So I guess some of the solutions that we can theoretically resolve it, some other solutions, there is no GR physics, and black hole is not really a black hole. And that can actually be tested. Well, to a point. Okay, other problems? Yes?
The lack of CP violation of instructions.
Yes, lack of, okay. So CP phase and this is the one in front of this term in the Lagrangian, is unnaturally small. And when I say unnaturally small, we are talking like 10 to the minus 10 area. And technically, the phase can be anything from 0 to 2 pi. There's really no reason why it should be 10 to the minus 10. And axions is actually one of the solutions for it. So, and this is generally referred sometimes as a strong CP problem. Okay. Others, I see a lot of hands before. Yes? Dark matter. Excellent. Okay. Dark matter belongs to an interesting class of physical theories. The observational evidence which we get, and there are numerous, and I will actually discuss those, appear to show that we're missing about 85% of all matter in the universe. And out of the total matter energy composition, we seem to be missing 96%. And it is possible, of course, let me see if I actually have it on the next slide or not. Okay. People have tried to explain all of those various observational effects by modified gravity. So far, no one has been successful. You can reproduce one of those, or maybe two. You cannot reproduce all of them. So for now, dark matter belong to a class of theory that we are all convinced this is true. So, and this is a very big problem, because we honestly don't know what the universe is made of. It's mostly not made out of standard model particles. Okay, others? Yes? The what symmetry? Supersymmetry is one of the, okay, so the supersymmetry is one of our possible solutions for what the dark matter could be. So the supersymmetry would be in this category. So supersymmetry is a possible solution for both the hierarchy problem and for the dark matter. Because the lightest supersymmetric particle has to be stable, it can be dark matter, it actually be perfect dark matter. And it's also perfect because then you can find it, because then you know it has to couple to standard model because it's been thermally produced. And also it will solve the hierarchy problem, because the supersymmetry actually have the following trait. To every particle, to every boson, there is a fermion, to every fermion, there is a boson. So all of those diagrams, which do not cancel, now sort of do, because now you actually have a term with an opposite sign for every particle, and all your quadratic divergences suddenly become logarithmics, and we know how to deal with logarithmic divergences. Does that cover what's been suggested? Okay.
I mean, my thinking with supersymmetry was that from a mathematical point of view, it's a natural thing to have.
Okay, so whether supersymmetry is natural, excellent, okay. So then we'll write it to this class. Whether it should naturally exist, and then it will solve, whether it has to be a feature of the universe, and whether that will solve the other problems. Excellent, others? Okay? Higgs potential instability. Okay. That could be either here or there. Well, and whether our universe will suddenly collapse to something else. Whether we actually, is that was the question, whether we have an actual true minimum or not a true minimum of the Higgs potential. Yes, that's a very interesting problem. Okay, others? Okay. Okay, okay. I'm going to say, write it right here, this. And there are two different things here. And I'm just going to say, because there are two separate problems here. So the first problem is this, that we know that actually universe expansion is accelerating, and something needs to explain this. There's nothing in the standard model which could explain why the universe is accelerating. And that actually been confirmed by different sources, from the supernova type 1a, from the galactic clusters, and from the CMB. So, and one of the possible solutions for that is just, okay, just add the cosmological constant. Now, this is fine. We can add the cosmological constant. People are kind of slightly reluctant to do so because that's the third or fourth time we've been doing it, and solutions have been found for the previous cases it did not need. So that's not the first time we are trying to actually add a cosmological constant because we actually don't understand something about universe. So people are slightly cautious here, but perfectly fine. Okay, there is a cosmological constant, but we can make a very simple back-on-the-envelope calculation. So what is a cosmological constant? The most trivial that, okay, it's a 0-point energy. It's a vacuum energy. And then let's compute the vacuum energy. So for cosmological constant, I think it's a level of 10 to the minus 3 eV-ish something. So to the fourth. And then the problem is, if we actually start, so let me see, in Planck's masses, that was, I think, 10 to the minus 60 Planck's masses to the fourth. Okay, I need to check on that. I'm fairly sure it's correct. If we just do back-on-envelope calculation that for the standard model, what is the vacuum energy, we end up with a value which is about, whatever, depending who is calculating, well, at least 60 orders larger than this. So it's very hard to believe of canceling things to 60 decimals. So somehow we may come to the point that the vacuum energy is 0 in a standard model, period. But then somehow we have to explain dark energy. To explaining why would cosmological constant have such a small but non-zero number, it's very difficult. It's very unnatural. And you can start at the non-standard model particles, but it doesn't matter. And that's pretty much it. Just it's just a standard integral. You can assume that all your standard model fields are harmonic oscillators, and then just integrate what the vacuum energy would be. And pretty much it goes as UV cutoff. So you're some sort of UV cutoff to the fourth, and let's say this is 1 TeV, and the cutoff, it's essentially, let's say that's a physics we sort of understand. And that's, there are many, many orders of magnitude here. So, okay, so there are two separate problems. That something has to account for the, am I wrong here? I'm writing those numbers from memory. There is other something has to code acceleration expansion of the universe. Nothing in the standard model can. This is effectively anti-gravity here. And if it is a cosmological constant, why is that so small? Does it cover the cosmological constant? Okay. Other. Okay, go ahead.
If the standard model is an effective field theory, then what's the correct UV completion?
Okay. Excellent. Others. Okay. Yes, why other 3 generations? Actually, other 3 generations. We're relatively sure there are 3, but we're not sure. Let me erase this. And other 3 generations. They may be forced, but so far unlikely. People have tried to estimate how many neutrinos are we allowed to have in the early universe. And the numbers seem to be come out that 3. And there are 3 neutrinos, there are 3 leptons, there are probably 3 quarks at the same time, because you kind of have to actually do the proper symmetries. But why do we need muons and tau? I mean, there is nothing in atomic physics, that nothing you make, the universe technically, you can make them out of the first family, and that seemed to be okay. That did not happen. As to why. Okay, others? Yes? Inflation. I'm going to write it here. And inflation covers a lot of things. And one of those experimental facts that our universe, it's about flat. And it's very difficult to explain. It's almost exactly flat. To actually, I think, at least a couple of decimal points at this point from the Planck data. And there is no rational reason why it should be. And there are many other things. There are monopole problems, etc. There are also the question as to why the CMB is so extremely uniform. I mean, we have only, 10⁻⁶ variations and so on. And inflation explains a lot of problems. However, inflation also causes a lot of problems. Because apparently, it's pretty hard to actually start inflation and then finish it. So with a modern theory of inflation, when you start inflation, you just keep making universes. And in one case, you're producing multiverses. And that can explain pretty much that entire list. Because if there are multiverses, we are living in one on which we can live. And that is kind of sad for particle physics a bit, because now a lot of great problems kind of go away. And there is those really dirty words, anthropic principle. But let's face it, the values of fundamental constants are very highly fine-tuned. Who knows how much we can change alpha? So the alpha is a fine structure constant. Who knows the value? 10137. Isn't that weird? Why? There's no rational reason. I mean, why not 1/32? Is that okay? I can make it 1/32? No. What?
It's my birthday, that's the reason. 13/07. My birthday.
Okay, excellent. Does anyone know which happens if alpha was 1/32? Would we be here? No, because you can't make carbon. If alpha is 2% different, you can't make carbon. I'll show you the process. Because if you ever looked at the different nuclear binding energies, it's very hard to make carbon because you need 3 helium nuclei to make carbon. And 2 nucleus meet, and then there is a beryllium resonance. And the value of this in existence of this beryllium resonance, that it exists for a very short time while 3rd helium nuclei will hit it and makes carbon. That's actually fine-tunes alpha to about 2%. It also fine-tunes strong interaction constant in the appropriate energy range to 0.1%. And I mean, you can change both at the same time, but you can't change either one. Also, if you make alpha about 110, you can make carbon, but then it will explode. You have a different problem because your your repulsion force will just tear the nuclei apart. And this is bizarre because there is 60 orders of magnitude. I can make those constants, and that's exactly to 2%. That is a bit bizarre. So I'm going to add this fundamental constants here, since we talked about it. Okay, others. Yes?
There's also the problem of their unification. So whether or not the coupling constants unify at finite.
Yes, unification. Okay, so I will write values, unification, and variance. Actually, variance I'm going to write here. Fundamental constants, constant. They're probably not constant. The reason why they're probably not constant is because every attempt to unify fundamental interactions results in theories with extra dimensions. If we have theories with extra dimensions, and then we would like to compactify them to 4 dimensions, if we actually have any dynamical fields involved, then your fundamental constants here are not true fundamental constants. It's the fundamental constants in your many-dimensional space which are true fundamental constants. And then dynamical field will cause automatic changes in ours. So many BSM theories would cause variation of fundamental constants, generally all of them at once. I will actually talk about various experiments which can test for it at this point. Okay, others? Yes? Presence of accidental symmetries. And it's possible that this hierarchy problem and strong CP problem, it is a consequence of accidental symmetries, for example, as well. But there are many other things which could be as well. Okay, others?
Yes, there's also a small issue with
The what?
anomalous magnetic moment of the muon.
Okay, muon G minus 2, okay. Now we got to puzzles, experimental puzzles. Okay, excellent. I will show slides on this. So when we're done with the list, I will go over those in some detail. Okay, others? Yes?
Why there is a hierarchy between random masses and mixing angles, the flavor problem.
Flavor problem, yes, okay. Actually, the whole fermion masses. Okay, I'm going to, write this one. So all the lepton and quark masses, yes, we actually first we don't understand why they are, what they are, and also they are funny. They really, the way they distribute is very strange. Does that cover it? Or is there some anything more of a flavor problem? Okay, so there is various. Yes, yes. So fermion masses. And the differences between the generations. Okay, others? Yes? Lepton flavor universality. I'm going to write here. Okay. Okay, others? Oh, almost exhausting. Anyone else? Yes? Charge? Charge quantization. Yes, this is an interesting one. There is no particular reason why charge is quantized. It just seems to be so. People have been looking at Milli charges for a long time. Milli charged particles is one of the explanations of the Idris results, for example. Anyone else? Okay, so we've been there at an hour, so I'm going to make a 5 minutes break. So, and then we will actually, I will show, let's actually, if you would like, you can take a picture of this, for example. Or I think we actually have, we have recordings of slides. And I will show then my list, which I think I missed a few things here, but I think there are a few additional things as well. 5 minutes. If you have questions, you can come to me. I will go over in detail. And the group assignment assumes that you will form groups of about 6 people. So if you already know someone and decide to kind of start organizing in groups of 6, you're welcome to start now. I will explain, at the end of this lecture what the assignment would be. It's hopefully be a fun one. But I don't know if some of you know someone or some not, if you will have say a lunch to form the groups. So if you already can start formulating groups as you get sitting in, to be in the same group, you're welcome. I will give detailed explanation, and you will have a link to my site also explaining this as well. Okay, let's try to sit back. Okay, are we having most of the people here? Okay, let's have them come in. So first, thank you everyone for participating. That was excellent. So as I said, it would be great if people ask questions. I know it's difficult and ask, then, but I'll do my best to hear you. Okay. So first, this is an excellent list, and actually I omitted a few of those in my list. So the reason why I've been writing them in different places is that if we really ask ourselves, what are the reasons to introduce beyond the standard model physics? Then we'll classify different questions in different categories. And first, none of that is absolute. This is kind of my classification. Also, I took it from the Peter Graham's talk, which was in GGI on quantum sensors here. So why to introduce beyond the standard model physics? The first thing that we just have to by observation. And this is kind of this category. I mean, you can add inflation to that list as well, just because it's really an explanation for a lot of observations. Then we have dark matter, accelerated expansion of the universe, matter-antimatter symmetry, neutrino masses, and we may discuss whether some of the other things belong to that list or the other list as well. And then we have, problems with really a lot of unnatural values of standard model parameters. Because you have to remember that in standard model, in the very smallest version, you have 19 adjustable parameters. These are not computed, cannot be computed. We do get them from experiment. So there was a hope that they can be computed, for example, string theory and so on. So far, that does not seem to be the case. So as of now, we do not have a theory which allows us to predict the values of fundamental constants. And here we have cosmological constants, heat mass on VV fields, a strong CP angle, all the masses of quarks, leptons, numbers of families, constants of fundamental interaction, etc., as well as several other problems which I have not included here. Now, there is some difference between the first and the second. Here we absolutely must come up with new physics. Here, as I said, there are alternative solutions. Whether there is fine-tuning on our universe or not, or that's the way the universe is. So, but nevertheless, it's important to try to solve this problem because quite possibly new physics exists and those problems are indication of new physics. But this is not exactly at the level that must be so as for those ones. And again, this is a matter of personal opinion here. So different people can list them in a different, so by no means take that as an absolute. So I would like to go over a little bit one more time. I put some slides, and I would like to go over a little bit about the experimental evidence for dark matter. So the first one, it's the fact that the rotational curves of galaxies are flat, and that's been known for a very long time. Generally, you assume that the further the star from the sun, then the velocity should go down as a 1/the square root of radius. It does not. And one explanation of this, and that actually is something which has multiple explanations, but one of them is that our galaxy is surrounded in a huge spherical halo of dark matter, which you do not see. Then, who knows what that picture is? Raise your hand. Okay, the bullet cluster. So, and it looks like sufficient number of people know this. So, two clusters collided and passed through each other. So this is a hot gas. Hot gas has friction. So as you see, this is actually significantly offset from where the mass is. Those are actually gravitational lensing data where the mass is in those galactic clusters. And as you see, they're not in the same place. So the one explanation is dark matter, because dark matter is mostly not interacting. So here we assume no more than one collision per the cluster. And actually, that's actually what gives limits on self-interactions of dark matter. For most part, dark matter behaves as stars. So one star can hit each other, but the probability is very, very small. The gas, however, has friction, so it's offset. Now, this is extremely hard to explain without dark matter. I'm actually not aware of a single explanation now that neutrino masses are actually under 2 eV. But the most really convincing argument for dark matter, it's the simplest fact that we are here, that galaxies exist. You simply cannot start without dark matter at CMB and make galaxies by now. So if you start at CMB, and this is a redshift of about 1100, and if you start with the overdensity is about 10 to minus 4, the overdensity, while they're small, scale linearly with redshift. Multiply those two numbers, and we are still at delta rho about 1. No galaxies by now. And this is really the most convincing explanation, the fact that large-scale structure look exactly as they're supposed to. Remember, normal matter cannot cluster before CMB because it's charged. It's only after CMB that actually neutral hydrogen forms. Dark matter can cluster essentially as soon as it cools down sufficiently that it no longer annihilates much. So, and there are many other things, but this is really some of the critical results, and this is essentially, there are no explanation for those two. And now, accelerated expansion of the universe. So this is actually supernova type 1 data, which are standard candles, that appears to be that the universe does not decelerate, it does not just coast, it does accelerate, and this is our explanation now that we think is either cosmological constant has to be added, and that creates a lot of problems as well, or there has to be a dark energy, which could be a quintessence field. Now, the hierarchy problem, weak scale. As I already mentioned, that for the Higgs mass, this is a top quark loop correction, and somehow you need to cancel not only this, but every other of them, plus all possible new particles, and also this is energy dependent at all energy scale. And one way to do it, it's actually do it with supersymmetry. So for every fermion, there is a boson, and you can cancel essentially those things out and end up with logarithmic divergences. But, and that leads to TV scale physics. This is essentially what LHC was built to find. Okay, and solve many, many other problems, and of course measure a lot of beautiful things. And I so much hope that we actually see new physics at next run. Okay, let's hope so. However, there are many other explanations, and one of them involves no physics at the TV scale. Who've heard about relaxions? Okay, a number of people, good. I'm going to have a very, very short explanation. So here's your Higgs field, and okay, it's infinitely heavy to start with. It starts rolling down, but there is an additional scalar relaxion Higgs-dependent mass. So there is a back action to the Higgs. So eventually, this Higgs evolves, and that actually causes a modification in the potential, and the potential starts having wiggles, and eventually Higgs just gets stuck in them. That results in a new particle, a relaxion, which could be light, and results no TV scale physics. Now, there are various loopholes here, but people have been good in closing them so far. This is pretty recent. I think the first paper was 2015. I actually collaborate with Gilad Perez on this. So this will couple to standard model via Higgs, and relaxion will actually have both scalar and pseudo-scalar coupling because it couples through the Higgs portal. It can be searched with pretty much all the precision physics experiments because it essentially can couple either like axion or like a scalar. And it could be dark matter. It has to be above like 10 to the minus, I think, 11 eV for that. So that actually would be alternative solution entirely to both the hierarchy problem and to the dark. It has a pretty hard to reach parameter space. Okay? Now, I already mentioned fundamental constants, okay, blowing carbon either apart. And this is actually, I want to show you, this is a triple alpha process. So you do make a resonance. That's the only really way to make carbon. This is extremely fine-tuned reaction. That would be bad. And now, and then I have this long list of all the other open questions, and that's pretty much we had here. The gravity and quantum mechanics. Also, we have not listed it here as any violations of Einstein equivalence principle, and that consists of 3 parts: universality of free fall, position invariance, Lorentz invariance. By the way, you assume that every time you compare any experiment, Because if that's not true, the clock in Japan and the clock in Florence will not work the same way. It will depend on where the clock is, what type of atom is being used, and also on the rotation. So that actually being assumed. And also we have not really spoke about violations of fundamental symmetries, the CPT, permutation, symmetry, or spin statistic connection. Yes, bad things happen to quantum field theories when you're starting violating those, like losing gauge invariance, etc. But nevertheless, that's actually a symmetry which we consider inviolate right now. People have been looking for violations, all of them. So essentially, this list is kind of postulates of modern fundamental physics, and it's possible or not, but not necessary to violate them. So any questions on those? And then there is a list of puzzles. So first thing, when we talk about dark matter, I would like to mention very specifically that they could be just new particles, because honestly, solving all of these problems generally generate new particles, which is very small fraction of dark matter. They could be the whole dark standard model out there. So there is a somewhat more default search for new particles which are not necessarily 100% dark matter, and also you need new mediators. There could possibly new fundamental interactions as well. So I kind of put them a bit separately because people generally connect new particles to dark matter, but you don't have to be so. The other thing which you have to wonder, let's say you find a new particle. How do you prove that that's dark matter? Okay, in case of WIMPs, there is a connection between production and detection. So somehow assuming, all of that is model dependent, but somehow assuming that you know the cross section and you know the mass, which is very difficult to decouple, but let's say you can, and have a lot of information with different types of experiments, maybe you can actually prove that it's 100% dark matter, but it's not necessarily quite so. Because there are many ways of avoiding some of the direct links between production and detection, even for WIMPs. For ultralight dark matter like axions, there is no link between detection and production. And in principle, you can produce dark matter gravitationally, and then even though it's difficult but not impossible, in this case, there may be no connection to the standard model besides gravity. So in this case, this is a very interesting question. With axions, you probably need to also see solar axions to try to separate the coupling constants from the masses. And even in this case, it's very hard to prove that something is 100% dark matter. So that's an interesting question as well to just ponder about. But for now, we'd be happy if you just unambiguously see new particles, because then we can start decoupling them. And now, and it's interesting, only muon G-2 has been picked. There are various experimental and observations anomalies. Some of them are very persistent. And I thought I will actually, again, starting talk about tabletop experiments. Some of them actually tabletop and some are not tabletop. Let's discuss what happens when we actually see the hints of new physics. And how do we proceed in terms of sorting out whether it is or is not new physics. So who heard of proton radius puzzle? A few. Okay, that's the one which had been resolved. But it just was very hard to explain with new physics. Okay, and this is not quite tabletop experiments, but some of them are tabletop experiments. So I'll talk about this one first. Okay, that's how our anomalies kind of look like. Okay, maybe something is there. But how important that is not obvious. And probably even on your undergraduate career, you already have seen a few things appear and disappear. There are many puzzles in both lepton physics and specifically neutrino experiments when you have 2, 3 sigma or more, like mostly 2 to 3 sigmas, and they kind of come and go. Some of them are persistent. So most I will talk about which are above 5, close to or above 5 sigma and has been persistent. So how do you measure the radius of the proton? First, you have to agree on definition, but once you do, you can actually do fairly simple, well, it's not simple, but fairly straightforward thing. The radius of the proton affects the hydrogen energy levels. Because there is a finite size correction for the time electron spends inside the nucleus. And if you actually don't think in quantum mechanics, your brain freezes when you think about how can an electron be inside the nucleus. Okay, it's a wave function. There is a distribution. There is non-zero probability for it to be inside the nucleus. And then what you do, okay, you measure transition energies between different levels. You calculate all corrections. You need to know QED really, really well. And then you extract the corrections to the energies due to proton radius. Remember, you need experiment and you need the theory to the same number of digits you have experiment. Now, this is one of the reasons I'm an atomic physicist. I love being able to actually compute things and have some reliability that actually when experimentalists measure it, that should be to whatever percent, 0.5% or so on. But this is really many, many significant figures computation. Then you extract the RMS radius and you repeat for many transitions. Hydrogens have a number of transitions, of course, which you can observe, and you average. So that seemed to be a very standard model thing to do, right? Okay, what's a better way to do it? The better way to do it is to use muons. Just because muon is very heavy. It's actually the enhancement that's the ratio of masses to 200 to the 3. So this is a much, much more precise experiment. And that actually was done in the, and this is a fantastic story. So people got that funded just to measure the proton radius better, because it seems like such a great idea, right? They build a laser, and laser for this muonic transition, it's 6 micron. It's extremely hard to deal with. And they haven't seen anything. The idea that they were exciting the transition by a laser and they should just see then the decay of the higher state. And the photons were not coming out. So for the longest time, and they worked with it for years, for the longest time, they really have thought that they have not built laser rate. They built another one. And then eventually they were told, people, you're done. You're not going to get muons anymore. You need muons to actually, you need to be at muon facility. And they literally was like a week before Christmas, and people were just thinking and saying, like, the experiment is going to be shut down. They have seen nothing. They worked on this for years. And somebody said, well, maybe the proton radius is just wrong. Pretty much they were just plugging the hydrogen proton radius, getting the frequency, and that's where they were exciting. And they could do one more run. They could either turn it to the left or turn it to the right, and they just randomly tune it away from what the number should have been. There's been no reason to do it. They're just out of ideas. And they have seen the signal. It's over 4 line widths. So they really tuned it away significantly for where it should be. And that was named as a proton radius puzzle. I can show you. And this is like way over 7 sigma. So that was the hydrogen spectroscopy. That was electron-proton scattering, but that was not, let's say, not entirely trusted. And the CODATA is an organization which comes up with this nice card of fundamental constants. That's what you see in your textbooks and everything. And they averaged it, and that's where was muonic hydrogen spectroscopy. This is like 0.84, and this is 0.88. This is nowhere close. This is many, many sigma away in this CODATA sigmas. And their sigma is like almost 0 at that level. Okay, the first thing that everyone blamed theory, the QED. That's been recalculated, tested, people end up with the same thing. I have to say that I've actually gave talks on that when it came out. So now just if you actually get this hydrogen spectroscopy thing closed up, it's many, many different transitions. And that's why when you look at average data, get the actual distribution. When you see in puzzled, when many experiments are averaged, I highly advise you actually look at original data. Because that's several different experiments, and those are all the experiments, that's a CODATA average. And yes, it's an absolutely correct statistical procedure. But nevertheless, those uncertainties are not small. So, and this is a muon radius. So you see within 2 sigma, most of those experiments by themselves would be within the muonic radius. So the obvious result is to measure hydrogen. So those were pre-frequency comp late 90s measurements. And that turns out to be the solution. First, it's very, very hard to explain the muon radius, actually, the proton radius shifting that way. So it's very exotic. You have to end up with some like a lepton contribution to the proton or as a really weird new physics to do that. So, and that was resolved. It took quite a few years. Those are very difficult experiments. And ways they were remeasured. So this is actually another muonic experiment. You can actually do hydrogen or you can do deuterium. This is deuterium data. And the first new hydrogen experiment which should come out, it actually turns to be here and not there. One puzzle is that one of the new hydrogen experiments actually turns out to be here. We still need to sort out why that happened. It's not clear. A lot of actually new interesting things turn out about those experiments. And now this is actually one more hydrogen experiment, and this is actually electron-proton scattering. So here the issue was experimental measurements. People still do not understand why the old hydrogen measurements were quite wrong, or why actually this new measurement is so far away, but it's very clearly a technical issue at this point. So as you see, in this case, this puzzle has been resolved. All you need to do is just redo the measurements pretty much. So, any questions on this one? Yes?
How old were the previous measurements?
What?
How old were the previous measurements of electron?
Late 90s.
So
Not that old. But old enough that people, even though technically they're in a lab, couldn't figure it out. There were some weird interference effects which were not quite understood before. But that probably cannot explain why it's that off. Also, this is 1s3s. People still don't understand this one. So, and as you see, the uncertainty is still not great. But the people will sort this out eventually. So those are not that old measurements. Other questions? Okay, let's move on to unsolved puzzles. But this is kind of one of the strategies here. Okay, the signature here, there was a lot of still variations of the experiments, and it was very difficult to explain it with new physics. So it probably was not new physics, it was sort of understood from the start. Now, muon G -2 puzzle. This is a little bit different because here we're actually comparing not two quite different experiments. We compare a single experiment and now a redone version of that experiment now in Fermilab instead of Brookhaven with a standard model. So this is theory. However, this is really theoretical value of what muon G anomalous magnetic moment should be. And this is a result of white paper which has 180 people there. So there is a theory collaboration of 180 people which come up with this. Let's put it this way. There is some new results because from the theory standpoint, the hardest thing is sort out hadronic contributions because that you cannot explicitly compute until recently, and people have been using scattering data for this. And okay, it's again fairly old experiments in terms of scattering data. And there have been new, purely theory lattice QCD results for it, which are pretty much agreeing with experiment, but they're not all agreeing with each other. So there is, my understanding, there is no, and this is not my field, there's no, and I'm correct on this, there's no complete trust in lattice QCD here, but nevertheless, people are getting there. So this is for sigma. The new experiment confirms the old experiment. I have to make sure you understand this is the same experiment. It's been moved from Brookhaven literally to Fermilab, and now it just has more muons. It will improve. In theory, will improve, and we'll see what happens here. Again, this is was to the different side from the muonic proton radius puzzle. So they could never be explained by the same new physics. You could technically explain this by new physics, but we'll see what happens there. So this is unsolved at the point. Questions? Okay. Now, this one you probably have not heard of. Who heard about measuring gravitational constants? Okay, so this is just measuring G, and this is Cavendish type experiment. So you have a torsion balance with two masses. Those are test masses. Near them, there are source masses, and because of source masses, the whole thing slightly rotates, and that measures G. You can pretty much most of the experiments doing what Cavendish did. In fact, in about 20 years ago, people realized, they actually didn't realize that the tangent of that string in a vacuum is different. And at some point, Kadate was so frustrated, they pretty much downgraded the experimental accuracy to pretty much Cavendish's accuracy for a while. Eventually, that got resolved. But nevertheless, as you see here, those circles torsion balance type of experiments, they're getting better and better. And this is a pendulum experiment. This is new atom interferometry that actually will get significantly better soon. This is actually, I believe, done here at INFN by Guglielmo Tina's group of atom interferometry. And eventually, this is completely a third method. And I've just heard there is completely a new method. But you see, this is the average. And there is a scatter all over the place. I've been on one of those meetings because I'm a guest researcher at NIST. And people really brainstormed of how to sort this out. Those people who do those experiments, they do only that, and they've done it for decades. They do not understand what's going on. They literally brainstorm ideas like, maybe we should just exchange people and labs. Like, you go to my lab, and I go to your lab. I'm not kidding. Now, this is experiments when if there is like a small mountain near your experiment, you have to know about it. So a lot of those are actually deep underground. Even that actually, you really need to know gravitational potentials here. But that's been accounted for, that's been measured, and they do not understand what's going on. And those are actually multiple groups, different multiple things, and they're not agreeing with each other. Pretty much everyone believes it's standard model. That's probably why you haven't heard about this. But nevertheless, this is extremely frustrating. We don't know the gravitational constant to more than like 3 significant figure, which is amazing. Questions? Okay, and those are kind of sort of tabletop experiments, I have to say. And now to the Hubble tangent. Who've heard about this? Okay, lots of people heard about this. So you can measure the Hubble constant many different ways. It's probably hard to see, but you will actually get my slides. I posted all the slides on my website. I'll give you the link. So this is from a recent review. That's the early measurements. Those are non-direct measurements, pretty much from the CMB or BBN. And those are current measurements like galactic clusters, etc., Cepheid stars. And this is now 4 to 6 sigma. The beta measurements seem to be resulting in worse agreement. And there is a huge review which tried to sort out what possible solutions actually work and what do not. They literally have a table with check marks. You do this, you can explain this. You do that. Like, for example, decaying dark matter cannot explain this. So people have looked at it, and this becomes trouble more and more people. Because honestly, there are several early universe puzzles, because now we can see further and further back in the past, things which we think we understood, apparently we do not. One of the puzzles in the early universe, it's how old are quasars, which are seeing. At this point, we literally can see all the quasars in the universe, and those are supposed to be active galactic nuclei, the supermassive black holes, which keep eating stuff. The rate of how much that supermassive black hole can eat matter, the rate of this is understood. This is a very specific, understood standard model computation. How much matter it can accumulate per time before it actually starts radiating more than it accumulates. Because those things are accelerators. And apparently you have those quasars which should take more than 1 billion years to make, which are only 600 million years old. And you can get stars before 200 million years. So it's unclear how to make them. People have ideas you can actually collapse the entire galaxy to the supermassive black holes without actually accumulating black holes to start with. So there are various solutions. We don't understand how it works. So there are other many puzzles, and I think the telescope will either solve or add more to those. There's interesting new results coming out of Webb. Okay, any questions? Yes?
Average means that your average is above
Right. So I think ultra-conservative, this one doesn't have Cepheids and lensing, no lensing.
Fine, but the very small optimistic average, which is not very different from that one.
Yeah, from not optimistic. I think that means whether the 4 sigma or 6 sigma, depending which one you're comparing with. But again, I'm not an expert on that specific topic. Right, but I think it's essentially you're just taking this data and then you're omitting the ones which for some reason people have problems with.
Yeah, exclusions.
Yes, it's just exclusions.
I'm okay with that. I'm just remark that many of them are of the same size and they really have to combine
Definitely.
all of them to get
And you see the uncertainties are large, but it's not like a proton radius thing. They're not that large to actually overlap with that directly. So this is, I mean, problems to you for like you people to solve. Okay. And now I included the Idris results. Who knows the Idris anomaly? Really? I think that's one of the coolest ones. So this is experiment which what they wanted to do is to find the age of the first stars. So how would you do that? Well, there is a 21 centimeter line. 20 centimeter line, it's a hyperfine splitting of hydrogen. It's 25 centimeters here on Earth. When you have the redshift of about 30, that shifts to radio frequency in megahertz. It's very, very hard to measure anything radio frequency on Earth. So that experiment is like a meter radio telescope. It sits in the middle of a desert in Australia, hopefully as much away from radio signals, not that it does all that good, but at least there is some effort to remove the background. There is also galactic synchrotron background, which is also has to be removed out of this. And in my understanding, this is one of the big problems. However, that had been published in Nature, so it's been significantly peer-reviewed. So now, why do the first stars have anything to do with hydrogen? When the universe is dark, the hydrogen is neutral. And the balance between the ground state of hydrogen and the upper states for the hyperfine splitting is well understood. So it's pretty much you can calculate how cold the hydrogen is. And that rate is understood. Now, when you actually have the first stars, what do you have? You have ultraviolet lights, the Lyman alpha, which is emitted by stars. This is through a somewhat non-trivial process, changes the population between 0 and 1 levels of hydrogen, of the hyperfine sublevels, which means that now it can start absorbing the CMB. So what you see, it's absorption profile, which starts at about 160 million years, and that's therefore kind of the time of the first stars, and eventually it ends because you just have too much ultraviolet radiation and it actually reverses itself. The problem with this is extremely deep. It's almost a factor of 2 deeper when it should have been according to the standard cosmological model. And I think there is a general agreement in the community that this is experimental problem, not as much experimental problem as an analysis problem. There are several experiments which are going to be online soon. There is also effort to place one on the backside of the moon, which takes care of some of the radio problems. So I think it's Lucid Diaper satellite, which is scheduled, I think, 2025, 2026. It's just going to hang on the backside of the moon and do this as well, according to other things. And there are several other efforts as well. So we will see. Now, if this is true, this is absolute signal of BSM physics. Because there are 2 ways of making this happen. One, you need to cool hydrogen more than you did. The only way to do it is to make it interact with dark matter, because that's the only coldest reservoir which you have at that time. It's also very, very hard to model. So mealy charged particles resurface because of this. This is one of the possible solutions, but they can't be 100% dark matter. And then the second possibility is that you shift the tail of the CMB so the background radiation is hotter than expected, which messes up a lot of, it's very hard to not mess up everything else when you do that. So this here, we are actually waiting for future experiments. So I think this is actually the cool one. Because look, if it's true, you do two things. You establish the time of the first stars, which are millions of years earlier than it should have been, 100 million years earlier than it should have been. If you open like old textbooks, it says you 600 million years. You know, that's not true because we get quasars by that time. But 160, that's very early. And the second, you prove dark matter interacts with normal matter. Okay, 2 Nobel Prizes, perhaps. Okay. But again, talking to that community, despite the fact that it did get peer-reviewed okay, and etc., there are many comments on that paper. Okay, we'll see. Okay, so now to your assignment. Since it's a school, okay, one of the possibilities which different schools do is to assign homework. Okay, how many are students? Almost everyone, maybe some postdocs. Raise your hand if you're a student. Okay, so I assume you had enough homework in your classes. Okay, so I decided maybe we'll do something fun and also to kind of create a spirit of the community and get you to talk to each other. So the similar assignment have been done on LISA Nuclear Physics School, but we are going to do it a bit differently. So first, you should form a groups of 6. And you can do it now, at lunch and so on, but sometime, you know, early today. And then you're going to have this assignment. Let's say a private foundation decided to solve some of those problems. For whatever reason. I mean, Elon Musk or somebody else. And they decided to assign $200 billion for this. Okay? So they decided to do it in this way. 100 billion is the reserve fund, and they decided to get 10 groups of scientists in groups of, well, maybe more than 6. Those are your teams. And give each of them $10 billion. And they can build anything they want or organize anything they want with the only constraint that they maximize the chance of making a new discovery and solve one of those problems. So here's your assignment. Form groups of 6, elect a chair. So each committee can decide to allocate fund in any way they want, with the only goal is to maximize the chance of discovering new physics. So you are these committees. You should make a specific plan of what exactly do you want to organize, to build, to send to space. You can be as inventive as you want. You can, build telescopes on the moon, even gravitational wave detectors on the moon. You can establish universities. You can establish theory institute. You can decide to invest in one solution or many solutions to one problem. So you can pick one problem and just do one solution. You can pick one problem to do many solutions. You can pick all of the above problems and do everything. So because I would like to make it as easy or as interesting for you as you want to do without overstressing you during this nice place in Florence. But each committee should make a brief presentation by Thursday evening, 5 minutes. And make it with PowerPoint, so we'll show that here. And if we don't have time on a Thursday discussion at 4:30 or 4 p.m., then we'll continue on Friday morning as well. I think we will actually have to use Friday mornings. And here are the constraints. You have to make a list of what is that, your ideas are, how you're going to be solving those problems. Then if 10 billion is not enough, you can apply for remaining 100 billion reserve fund, explain why you need it. You need to list what problems can it potentially solve, how will it solve it, and for experiments and space missions, you should mark technology readiness level. So if anyone ever seen the NASA technology readiness levels, there are TRLs from 1 to 7. 7 is already goes to space. And I know, of course, many of you are theorists, or maybe all of you are theorists. I'm a theorist. So I designed those kind of very easily. The first level of technological readiness, we know how to build it, we just need money. The second level of readiness, there are prototypes and we need like 5-10 years of R&D to get there. The third one, there is a design with a number of problems to solve, but maybe it should be done in 10-15 years. 4, there's an idea, but we don't quite have an idea how to build it, but we're pretty much sure that we can build it. So at least it's not impossible at the present theoretical level. It's interesting which one of those muon colliders, for example, belong to. It's a thought. Number 5, theorists wrote a paper with a great idea. This is kind of the level like I'm a genius, not an engineer. Somebody else figures out how to build this. That's level 5. Let's say 30 years. And the second is kind of last one. Not sure what experiment will do this, but here what we need to measure. This kind of belongs as proof that gravity is quantum, kind of. Don't know how, but that's at least what we're measuring. And the last one, any higher level will be science fiction, so let's stop here. Okay. So, and I would like you to make, since you are given 10 billion, but you can get another 100 billion approximate cost. And here we are only looking whether it's 10 million, hundreds of millions, or a billion or more. Okay, let's see whether we can actually, I have it next slide, but let's see whether we can gauge some approximate costs. Okay, who can tell me how much LHC costs to build? 5 billion. The construction cost officially, if you, maybe you can correct me. If you do Wikipedia.
They say 7.
What?
They say 7.
Okay, if you, okay. You're okay. Right, okay, 5 to 7 billion, okay. Operational cost is actually 1.5 billion a year. So the CERN budget is 1.5 billion a year. I think 1 billion is just running the LHC. So, okay, Webb telescope. Anyone? Order of magnitude. Okay, anyone else? Come on, guess. Participate.
Maybe like a few 100,000.
Webb telescope?
A few 100 million.
10 billion. Again, if you Wikipedia, so. Okay, we just seen muonic G minus 2. Any guess in order of magnitude? About 100 million to 200. Okay, you have muons, it's accelerator facility. You're building accelerators, you're in 100 millions. Okay, atomic clock, 10 to the minus 18 experiment. 1 to 2 million. Here we start including not just experiments, not just equipment cost, but also like postdocs, grad students who have to operate this. So building a nuclear clock, that's 10 to 15 million. Building dark matter experiments, xenon 1 ton, or LZ. Ideas? WIMP experiments. Actually, surprisingly, apparently less than that. Apparently, LZ funding is 67 million. So I was surprised. That does not include digging large caverns underground at 2 miles. That's extra. That's just experiment. And here again, it's only construction cost. Okay, ice cube, neutrino detectors at the South Pole. Okay, that's kind of in between. The NSF saying 279 million for the construction cost. Again, in all the money, but so on. And let's say the last one. Who knows what the microscope mission is? Let's start sending things to space. Okay, it's equivalence principle classical mission in space. 140 million euros. And again, if you're sending anything to space, this automatically goes to you pretty much 100 million or above. If you're sending anything in a geo orbit, that's much more expensive. So this is order of magnitude, and I did actually make kind of your approximate list. Oh, hypercamera actually they're saying 700 million cost. So, and as you see, all of the kind of small experiments, sort of precision measurements, is like 1 to 10 million scale. In fact, my field laughs when they hear that 10 million, it's kind of such a small experiment, it's not worth the paperwork for the DOE. Because in my field, 10 million is pretty much one of the largest single experiments you can do. Oh, by the way, the Theory Institute, if you give 25 million to 30 PIs, it's a very small amount of money. It's like 100K a year. So if you're establishing theory institutes, you need more money. Okay. So this is your task. And I know that seems daunting, but I have decided that one of the reasons why I think this can be done is because the US just had a SNOMAS process. And this has produced a lot of documents. The SNOMAS, it's a particle physics exercise. And it lasts for a year. That entire community is separated from many, many different groups. So frontiers, the cosmic frontier, dark matter, dark energy, cosmic frontier, this rare precision experiment frontier, the accelerators frontier, instrumentation frontier, and so on. Each one of them produced a report. And then there is a highlights. So I give you the link to the hour-and-a-half video, which explains kind of US particle physics efforts, highlights in about hour-and-a-half in its entirety. So you can start there. Okay, so I have made a site for you. So if you just type my name, let me give you, so you can show where that is. So this is simply my name, Marianna Safronova /GGI. You can access it directly from my site. By the way, this is a lecture slides. We haven't quite got through that yet. And then I actually already put a few of the things for the next lectures, which will continue. And this is a school project. You can simply click, and you get this list, which you have seen online. And the idea is to be fun. The idea is for you to start developing a vision. Because as scientists, you will be on those committees eventually. For example, I have been on a decadal committee for the AMO physics. And that's a committee which produces a 10-year recommendation plan for the White House in the US, for the DOE, for NSF. This book goes to every single funding agency in the US and some abroad as well. I'm now on the NASA Biological and Physical Sciences Decadal Survey, which essentially NASA doesn't fund anything. They're just waiting until the survey is out, telling them what to fund. And all of those, of course, have to consider community input. And in order for you to consider community input, I have given you a number of links. I'm going to increase the number of those. So this is just linked to the SNOMAS. I will also give you separate links of the summary documents for them. And this is a talk on YouTube, physics highlights from all the frontiers. This is actually an example of kind of the presentation, which is a particularly well done. And here is something which we are looking for. Okay. So fundamental questions. Inflation, BSM degrees of freedom, is dark energy cosmological constant. Here is a Planck, LIGO, and different other experiments, and here is a list of specific goals which people have. And that's what's been built, and that's what they actually want to get to. So eventually, you can actually pretty much solve all of these problems. So this is something which we are kind of looking for. I will give you, so this is the example document for the cosmic frontier, for the CMB, and the dark energy experiments. So see if any of those experiments are interesting for you. If you have absolutely no clue what to do, you can always start with dark matter. Because for dark matter, or you can actually just build a net collider. Just make sure you list exactly what problems that's going to solve. So again, you can make it as easy or as complicated. This is something which also give you something to chat about. So I suggest already when we break for lunch, start forming groups of 6. And I also suggest that each group has to elect a chair. And a chair must make sure that in all of the group members contribute. Like literally, if you're a chair and no one is participating in not participating in discussion, ask the opinion. So I suggest that by kind of in a day, you select a problem or problems you want to solve and assign tasks to all group members. You study this, and I'll put more links for you actually. So I put some talks on dark matter, like 20-minute talks, they're easy to hear. I'm also, for that talk, I will, it's like hour and 40 minutes, so I'll give you the breakdowns, which frontier is where. If you're interested about accelerators, you can just listen to 10 minutes. So assign reading or viewing materials. I'll put like about 10, 15 more links in there as well. So you have somewhere to start with. I also put links to the reports. For example, there is a dark matter report from the Frontier, and you can just read the introduction and see what possible solutions are. Okay? Have fun. Thank you so much for your attention.